Okay, thank you, Guillermo. Thank you above all for giving me the opportunity of preparing this thing, because I decided when you invited me to do Colloquia, I decided I'm going to use. Is it okay?
Yeah, both on.
Yes.
Okay, thank you.
I decided to use the occasion for doing something which I want to do since a long time. Now I hope that I'm going to allow you to stay with me. And I have to correct you, actually. My involvement with Portugal is since 1992,
okay.
When I met first this guy. They actually allowed one of the projects which I was, one of the ideas which I had to be successful. Anyway, so in fact, the title is Through Measurement and Fault Discovery, because mostly I want to basically go through some sort of historic narrative about why, what are the current, I would say, criteria for being able to try to be sure that we are not being fooled whenever we make claims about scientific achievements. So, in fact, there's been extraordinary claims in the last years. I'm talking about the last 15, 20 years. We have, but you will see, I will also go further back in history. We have been confronted with widely advertised discoveries. In fact, this is one of the reasons why this is becoming even, I would say, more crucial today, because we are really in the spotlight of media. And I mean, typically we learn about things more first from the newspapers than from scientific reviews. So there's been the Higgs boson discovery. There were the superluminal neutrinos, if you like. I mean, I'm going to go through this. There's been gravitational waves, which has been a great thing. And now, as I said, I will try really to go through the criteria which basically lead to which are using to make discovery claims, and also through history to see how they have developed and see what are the limitations. Now, some definitions, I promise I will not be too technical, but I have to go through some definitions. One thing is that the likelihood function, simply sometimes called the likelihood, is the probability density that the observed data viewed as a function of the parameter of a model which we have on how things behave in nature is indicated as with this symbol, where x are the variables which are being measured and theta are actually the parameters of the model, okay, which are meant to represent the variable behavior. The likelihood ratio, which is the ratio between two likelihood functions, measures the degree to which the measured data supports one set of parameters versus another. So if you like, this is a way we check different models or different hypotheses. In particular, I would say that in our case, the most common use is to have one of the parameter set being the one which is the established model. In high energy physics, the standard model, for example. And the other is instead, so is the established theory. It is also called the null hypothesis. While the other set essentially represents the model of possible new phenomena, which can be typically coming from some sort of theoretical prejudice. There is a theorem which states that the likelihood ratio for large statistical samples will approach a chi-square distribution. So from the ratio, we can extract the value of, given the number of degrees of freedom, we can extract the probability that the model which we are looking at is correct. Now, the concept, how do we? The concept of statistical significance is a way to report the probability that an experiment obtains data which is at least as discrepant as those actually observed under a given null hypothesis. Okay, so by looking at the likelihood ratio. So the null hypothesis, as I said, usually describes the current accepted and established theory. So when looking for new phenomena, we use the likelihood ratio to test the hypothesis of new phenomena versus the established theory, standard model for high energy physics, for example. So the chi-square value which we obtain from the likelihood ratio represents the probability of obtaining a value of the ratio at least as extreme as the one observed if the standard model or if the null hypothesis is true. So given this p-value, how do we go to the concept of which we always hear about sigmas? So this is done essentially by finding the z, which basically such that the integral of a Gaussian functions defined between 0 and 1 equals p. In other words, it is a way of basically expressing the probability that something of what we are observing is actually true. To give you an example, 15.9% is one standard deviation effect, 0.135% is 3 standard deviation, and 0.0029% is the probability which corresponds to 5 standard deviation, which has become what we have called the 5 sigma discovery threshold. And I will basically try to guide you through the history of where we got to the 5 sigma and why we are using it. Now, let me go through first a success story. This is what led to, if you like, this is the search for the Higgs boson, okay, done by CMS. And if you like, the null hypothesis was the model represented by the blue curve, and the new phenomena hypothesis is the additions of this peak at a given mass. So it was not easy, and essentially that gives you also to give you just a background on what is coming up in terms of trying to figure out how to define significances in an environment where you have a lot of different possibilities. The probability to produce a Higgs boson in 2 proton collisions is 10 to the times smaller than to produce any other final state. Now, of course, things were actually becoming, I would say, very convincing, because we were not seeing it in a single channel. We saw it as well in the Higgs to photons. Again, here, if you like, the null hypothesis is this, and this is, if you like, is the new phenomena. And everybody started talking about 5 sigma. The reason being that, and you can see here the famous value of the probability extracted from the likelihood ratio, and how it behaved whenever you moved the hypothesis of the new phenomena, being the Higgs boson, as a function of the mass of the Higgs. You could see that essentially when you started going around 125 GeV, you had that the probability of this being compatible with the standard model without the Higgs boson started going below 10 to the minus 6. Okay? Or if you like, started going below what is called the 5 sigma level. So everybody was discussing about 5 sigma, and this was in fact the criteria which was defined in order to be able to say, yes, we have discovered something. Let's just some caveats. The whole construction rests on a proper definition of the p-value. Any shortcomings of the property of p, and I will show you examples when this was the case. For example, the fact that the probability density functions is basically what we call the null hypothesis is affected by some systematic effects, totally invalidates the meaning of the derived number of sigma. In particular, using sigma units does in no way mean that we are implying that the test statistics of what we are using for our phenomena are of Gaussian shape. In fact, here one has to be careful because sometimes people are led to confusion. In other words, the conversion of the probability value into the number of sigma is independent of the experimental details. In other words, it's simpler to use number of sigma instead of basically using numbers with many digits. In other words, we prefer to say 5 sigma rather than saying 0.0000029% probability, okay? So the birth of the 5 sigma criteria. It was born in the 60s when fundamental research was being done using bubble chambers, and essentially people were looking for really new particles and which essentially one was discovering, if you like, all of the zoo of particles and the way that standard model behaves as we know it today. So these guys essentially was looking at this, at what was happening around the world in terms of measurements of looking for mesons or baryons of new kind, and they were basically working out on, you know, obviously in order to start to reconstruct the mass of these new mesons, you needed to have either 2-prong, 4-prong, or 6 prongs. And whenever you look at all of the number of images that people were taking around the world with bubble chambers, and essentially taking into account that one would have order of 2,500 events, this was his estimate, of pictures analyzed per histograms, one would essentially end up with 15,000 histograms and 35 million mass combinations. So, in other words, you had a huge number of parameters and distributions, bins to look at, and it was almost unavoidable that you would get some bins which would fluctuate. In fact, in their paper, we're basically saying that one would basically see something, especially one would always see some sort of fluctuations, and in fact, if one looks at 150,000 histograms every year, one is capable of generating somewhere between 10 and 100 deceptive upward fluctuation. And so, for example, one would basically see order of 100,000 potential bumps per year, and one should expect several 4 sigma and hundreds of 3 sigma fluctuations. So, his conclusion was, if you want to be safe, you have to basically, given the number of distribution you're looking at, you should basically looking for 5 sigma effect, or if you like, looking for something which has probability of happening, which is 0.0000029%. So, and there's a recommendation for the experimental groups, which have spent years and $1 million for building their experiments. They should go ahead and publish their tantalizing bumps, or at least circulate it as a report, but they should realize that any bump less than about 5 sigma constitutes only a call for a repeat of the experiments. So this is the beginning of the 5 sigma requirement. So in fact, the first reason for the 5 sigma is the statistical fluctuations, okay? So the 5 sigma criteria is basically to protect against pure statistical fluctuation, because in fact, if you try hard enough, I mean, if you look at a sufficient large number of distributions, you will find a fluctuation. The number of trials required in order to reach the 10 to the minus 7 probabilities of the 5 sigma is very large. But on the other end, you know, in modern experiments like for Atlas or CMS, we are performing a very large number of searches. So we tend to correct, so we have to correct our significance by estimating the look elsewhere effect, which accounts for the reduction of significance due to the trials we made to find an excess. So if you like, this introduces the concept of local significance and how to correct it for obtaining something which is much more global in terms of assurance of seeing something which is true. Now, the brute force to estimate the Lucas-Ware effect is to simulate by Monte Carlo method a set of experiments under the null, or if you like, the standard model hypothesis, and varying all of the parameters with their precision and checked for the likelihood to have a significant fluctuation. In order to match 10 to the minus 7, one has to simulate order of 10 to the 7 experiment for each parameter set. So you can see that this is not going to be trivial. Now, in fact, when dealing with some of the searches at LHC, this can be practically impossible. The Higgs search implies, for example, a combination of dozens of different channels with hundreds of parameters which reflect experimental and theoretical uncertainties. So you would have to basically, if you were really to follow the brute force approach, one would never be able to converge. In fact, there's been asymptotic methods which have been defined to evaluate the Lucas-Ware effect, and I mean, this is the paper, and I cannot go into the details of it, but believe me, this has been, if you like, in modern experiments, is being taken care and considered very seriously as a problem. Now, let's go back to history and see how you can get it wrong. Some history about some of the major discoveries. So despite the fact that already in the 60s people were thinking about the 5 sigma in order to be able to protect oneself against statistical fluctuations, a rigorous approach with respect to discovery was not always enforced. The Jape site discovery in 1974, there was no discussion of significance. I mean, the peaks were too big for even bothering discussing significance. People were all convinced that we're seeing something new. The Tau discovery in 1978, there was a lot of discussions about the fact, I mean, this was something which was a little bit less established in terms of theoretical expectations. And so there was a lot of discussions about hadron backgrounds and things like that. And they didn't really discuss about significance, but they were more worried of being fooled by some sort of background. The Upsilon discovery in 1977 instead involved lots of statistical tests, mostly because the same group had discovered another thing 1 year before, the particle which became known as the Whoops Leon, which was Leon Lederman, which basically got fooled by this peak. And in fact, this was a clear example of not taking into account properly the Lucas-Ware effect. And they basically, it was the invariant E plus E minus mass in dilepton pairs looking at fixed target collisions of protons of 400 GeV. And by adding more data, they basically, the peak disappeared. So the fact that the same group had been beaten by this made it that they were requiring almost more than 8 sigma in order to be convinced that they were seeing the upsilon at that time. Okay, more history. The W boson discovery in 1983, there were 6 events. There was no statistical analysis, also because the thing was being pushed by Carlo Rubbia. But a lot of discussion about the fact there was no background. So essentially, there was no background. People could not discuss and think that the thing could be wrong. Okay. The Z bosons, it was 4 events still in a little bit later in 1983. There were 4 events. Also here, the discussion was mostly concentrating on showing that essentially after the final catch, there was very little background. Now, the top discovery instead is the first modern application of the 5 sigma criteria. In 1994, CDF published evidence based on a counting excess, which, if you like, interpreted in terms of p-value, amounted to order of 2.7 sigma in a B-tagged single lepton and dilepton data sets, and accumulating, and when you accumulate these 2 data sets, one get a mass peak which was over 3 sigma. In fact, this is where I think is one of the first instances where one started changing using 2 different words. One is evidence and the other is discovery. So evidence is order of 3 sigma. That was the mass that they were measuring, which was actually not too far from what is, today the mass is known to a much better precisions. Now, 1 year later, CDF and D0, with 3 times more data, presented the counting excess at the level of 5 sigma and claimed discovery. The important point here is, well, that the thing was confirmed by another experiments, and I will come back to that later. Now, let me make, now I think I've tried to convince you that we are trying to be rigorous, that we take into account local square effect today, and that we are able to calculate it and things like that. Now, this is a bit of a note about the local square effect estimation. There is a degree of uncertainty on how to define it. If one look, for example, at a mass histogram, and you don't know where you should try you don't know a priori where you're trying to fit a bump, but you're looking everywhere. One should consider the location parameter and the freedom to be anywhere in the spectrum, the width of the peak, in terms of, this is, if you like, some sort of theoretical prejudice about it, the fact that you may have tried different selection before settling on the one which you actually end up presenting, so essentially it amounts to having, if you like, different experiments. The fact that you might be looking at several possible final state and mass distributions, and different people in the experiment can be doing similar things with different data set. Should you count this in? Because maybe the guys who didn't do the analysis which you are publishing are not being mentioned into the paper, and there is an ambiguity in the local square estimation depending on who you are. The tendency on how to, if you like, apply personal judgment on the local square effect estimation depends on whether you are a graduate student, the experiment spokesperson, or the lab director, for example. Okay. The bottom line is that while we can always compute a local significance, it may not always be clear what the true global significance is. Okay, so that is to be aware. Now, the other reason for the 5 sigma criteria is to protect against problems with the modeling of the systematics behind the given measurements. And that is a completely other field. And one has to be careful because the 5 sigma, it is, I would say, very rigorous in protecting us against the statistical fluctuation. But when it comes to the evaluation of systematic errors, one has to be very careful. The theoretical models which are used to evaluate the null hypothesis could be flawed or incomplete. And I will basically show you examples about this. The subjective prejudice on the way to evaluate them can play a significant role. And something which many people assume about the fact that the systematic error is distributed as a Gaussian is often a very rough approximation, especially when you're thinking about theoretical systematic effects. So concerning model inadequacy, when looking at new phenomena, the discovery assumes a correct estimation of the null hypothesis, meaning that we are showing that the excess which we are seeing is with respect to what is predicted by the model without the new phenomena. And in fact, the limitation of theoretical modeling has been basically, can be due to many different things. Is the implementation of the theoretical model, of the theoretical understanding, or the understanding of the theoretical model by the experimental teams have been the source of false claims in history. Examples. The quark substructure. This is a CDF, basically published a paper thinking that they had basically repeated Rutherford achievement of finding that the quark was not an elementary particle, but it had a structure. And in fact, it turns out to be an imperfect knowledge of the parton distribution function inside the protons, which has led to this excitement. You can see this is actually the way these guys were trying to. So sometimes it's not trivial to interpret the data. New particles. Aleph observed in 1996 a 4 sigma excess of Higgs-like event at 105 GeV in the 4-jet final state. So So does it remind you something? I like the hopes, Leon, kind of things. And they published the search. They had 9 events in a narrow mass region with an expected background of 0.7. None of the other lab experiments saw anything, but we still ran the next year at the same center of mass energy in order to check it again. And the peak was not confirmed. In fact, it turns out that, for example, in Delphi, we could actually start seeing the appearance of such a peak if we dropped the cut on possible radiative return where the photon could hadronize to a rho in the forward region. But okay, this, not that this was the origin of it, but you can see that depending on how you analyze your data, you can get very different results. These bottom discoveries, so CDF in 1999 observed a significant excess of events with 2 or more leptons in dijet events. This is actually a very nice distribution. I mean, to remind you that the Higgs boson in gamma-gamma, and with characteristics which were very different from B decays. So, in fact, the evidence disappeared when increasing by orders of magnitude the sample. So here again, the number of sigma would have saved them, even though I think this was very close to 5 sigma. But that is the interesting thing, which is one is as well to be careful about. The news about this bottom discovery spread. So Aleph was actually informed even before CDF was making their result public about the excess, and they found a 3 sigma effect in their data, reported at the LabC in July 2000. In fact, again, Delphi was really trying hard to give them an hard time, showed that some problem with the Monte Carlo simulation, and that no excess was present in their data. And later, in fact, the signal was understood as an artifact of wrong Monte Carlo simulation and a miscalibrated electron identification rate. This was actually something which really got a lot of people busy, because I mean it sounded very convincing. You can see CDF collaboration saw a 4 sigma signal at 145 GeV. This thing, okay. While this was, if you like, the standard model of the null hypothesis in the anti-proton collisions, and the effect actually grew with data size. And I think it remained alive for a long time, order of a couple of years. It was eventually understood to be due to a combination of 2 nasty background contaminations which had not been taken into account. And there is subjective prejudice. So there's a certain level of personal appreciation in this estimation of the systematic errors is almost unavoidable. It can go both ways, adopting criteria which inflate the error, hence the danger of preventing optimal extraction of information from the data, or having an attitude too optimistic about the understanding of possible systematics, and so provoking false claims. An extremely dangerous effect is the Nobel effect in this respect. In fact, the example is the superluminal neutrinos. In 2011, Opera collaboration produced a measurement of neutrino travel times from CERN to Gran Sasso, which appeared to go faster than light in vacuum. The effect was at the level of 6 sigma. It was eventually understood to be due to, I would say, a trivial single large source of systematic uncertainty, which was a loose cable. Okay. There's been conjectures when talking to people of the collaborations that the haste with which the result was put out, I mean, they figured out that it was a loose cable within a couple of months after the announcement, was also due to the rumors about an imminent result coming from a competing US collaboration. So you can see clearly the N effect here. And now let me try to stress the importance of preliminary, which is sometimes not being taken seriously enough, especially by our theorist colleagues sometimes. We have grown accustomed to have a quick presentation of result at conference or lab seminars which are labeled preliminary, especially because we are not yet done with the analysis simply. We are halfway or say 3/4 of the way, but we are not done. Because the ultimate treatment of the data and the sophistication of the analysis has not yet being implemented. It always hides also the fact that the systematic errors one quotes for this result might be rough estimation, stemming sometimes from subjective judgment of what is still missing to achieve the ultimate results. In fact, the preliminary meaning has gone from not yet published in a peer-reviewed paper to very first look at the result with not yet completed calibration and systematic error evaluations. And it's mostly due to pressure, outside pressure from the lab management, funding agencies, and the peers which want to have a first glimpse at the result at the end of a run or for the closest round of conferences. I mean, you always try to time your results for the spring conferences or for the summer conferences or for the big conferences of the year. So one should really take seriously the word preliminary. The example is something which I've been involved directly, is the 750 GeV gamma-gamma bump. By December 2015, meaning the end of the round 2015, at the CERN Jamboree, it was noticed that there were, you can see here again, the p-value from Atlas and CMS, when looking at high mass combinations of two photons, one would get, a fluctuation at the level of 3 sigma. You would not write home about it, except that Atlas was seeing something roughly in the same area. So it's a striking coincidence. I mean, this is actually how the data look like, okay? And we basically, I think that both Atlas and CMS really refrained to make a combination which would have pushed things close to discovery level, because all of this was really preliminary. And we know the story. There were more than, in fact, more than 400 theoretical papers in 3 months, but I think more than 800 in the next 6 months. Excitement in the media, but with 4 times more data, it looks like a fluctuation. Whenever you looked at it the next summer, there's no clustering around 730, 750 GeV with 4 times more data. 2016 data is consistent with 2015, and it appears that 2015 excess was a statistical fluctuation. This is the statement. Now, the real story, let me share with you the real story, given that I know it. There was never a match between Atlas and CMS excesses, because essentially, once you calibrated correctly the electromagnetic calorimeter, Atlas was seeing a fluctuation which was something like 30 or 40 GeV away from where the CMS excess was. And the resolution we have on these things is GeV. So, I mean, if you are 30 or 40 GeV away, you're basically seeing fluctuations. It's as simple as that. It turns out to be completely random, the fact they were close. So, let me go through another aspect of this interpreting the statistical significances. I've purposely stayed clear of the minefield discussion between statistician and high-energy physicist, namely regarding how to communicate scientific results. We tend to use the frequentist approach of using likelihood ratios as test statistics, as opposed to present ratio of probability of null versus signal probability weighted by our prior confidence on the models, which is a Bayesian approach, okay? The one thing to be said is that we are basically presenting all our data as, in a frequentist way, but if you think how the way we think, the way we deal with things in our everyday life, the minds of humans are Bayesian in nature. We have priors about the probability which we assign to different hypotheses. If our prior belief in the alternative were low, we would still have a bias towards the null, even with the large evidence against it. And this is actually, I like this plot, which is the Ligeti. The first one was done by Ligeti. This is updated in 2016, and probably this is yet another update. But this, even if it is old, it gives you it explains what I want to mean. So the trust in deviation depends on the reliability of the theoretical expectation. Here we are talking about flavor physics, okay? So there is a new phenomena in flavor physics, like, you know, top decaying to quark and Z, H decaying to tau and mu, violating lepton universality, and so on and so forth. You can see these are all sort of possible new phenomena in heavy flavor physics. And you can see that this is the number, this plot shows the number, the significance one would need in order to be able to be convinced that you're seeing something, versus what is called theoretical cleanliness. In other words, how well is the theoretical modeling and the calculations which are behind the given possible exotic phenomena. And you can see that you need to be here to be really convinced that you are seeing something. And this, if you like, this is what I call the Bayesian mind bias behind what could be a claim for a discovery. And in fact, this is a table from Louis Lyons, which this is completely personal of Louis, essentially looking for possible new phenomena. And identifying what essentially, if you like, it could be the surprise level, what would be the impact in our understanding of nature, the look elsewhere effect, the systematics, and the number of sigma he would need to be able to believe that any of this is okay. Okay, and you can see that depending on his bias about what is the impact. As opposed to the systematics of the measurement and also the surprise level. For example, for SUSY searches, he would basically not trust anything which is less than 7 sigma. And for finding neutrinos which are faster than light, he basically says it's too high to be quoted in terms of number of sigmas, okay? Because he would never believe it, okay? So, where are we now? Let me conclude by giving some sort of trying to figure out where are we and where do we go and what we have to be careful about. The present situation is that, especially with the discovery of the Higgs boson, we have laid the keystone of the Standard Model cathedral. Okay, so we have a beautiful built cathedral. We probably would like to get a sharper picture of it, but it is very nice, okay? But we know that there are still some fundamental problems. So there are unanswered questions. One of the major one is gravity. The difficulty to reconcile quantum mechanics with gravity has been a theoretical nightmare since 100 years. Dark matter is something, again, we have no clue about, even though we know it exists. Why we have only essentially baryonic matter and not antibaryons? I mean, why do we have matter? Why is our world made of matter and not of antimatter? Is another question to which we don't have a complete answer. And you could actually extend this in terms, if you want to really look for questions which could yield surprises, is why there are 3 families of fundamental particles, what is the structure of the neutrino sector. The Standard Model itself seems to indicate that something is missing. I mean, you know the naturalness problem, which is the fact that we found the Higgs at 125 GeV is very difficult to justify theoretically, because essentially it is not protected by any new symmetry, which would, the natural way would be that the Higgs mass to be the Planck mass, and then one has to go really through loops in order to justify this. So, in other words, you have a beautiful cathedral, but when you start looking from a distance, you see that there is something else which we are not really understanding. I presume you all have seen Avatar. So, there's clearly some new physics behind this, if this were to be true. And in fact, there is, this is an old slide. And probably most of these theories have now been negated, but still it gives you an idea. What is the way people are trying to address these questions, which we don't have an answer yet. Okay, so it's really a complex scenario when you look at it for example, on the theory side, how people try to find answers to the questions which I was outlining before. And relations between theory and experiment is actually something which has been seen in different ways if you are a theorist. So this is seen by theorists in terms of relations between theorist and experimentalist. Now, this is more seen by experimentalists in the sense that you're really, I would say, disqualifying theorists almost every day with our measurements. And it is the situation where we are now. So, for the future, so we are sure, I think we are reasonably sure that there are new phenomena. Is the 5 sigma criteria safe criteria to avoid inventing something new? I'm not really convinced. It's necessary, but probably not sufficient, because it requires a lot of experimental care. So I think that we should really watch out for possible fake peak at 5 sigma in the future at LSE or also other scientific programs, especially if they're coming from a single experiment. I hope that I've convinced you that having 2 experiments has been very beneficial in the past. So, and to summarize, I mean, is that understanding nature has always required improved tools and measurement devices. The complexity of today's instrument and the sophistication of the measurement which we are doing in terms as well of technique requires a really rigorous approach to understand the detectors we are using and the backgrounds which we are expecting. We have developed a deep understanding of the pitfalls to avoid from the errors of the past. And I think that the fundamental principle of the necessity of having more than one experiment able to perform the same measurement has been proven over and over again. And I think we are all ready to exploit fully our data to make discovery if nature is kind with us. Thank you.